Okay, we're in the world of solving compound inequalities and absolute values, compound absolute values, but right now we're working on compound inequalities, and we are going to solve an OR compound inequality, and this is going to correspond to example 2, which is located on page 42 of your textbook. Now, one of the things I like about OR compound inequalities is this little word right here. Or. I know that this is an or inequality. I don't have to guess. I don't have to look for things being sandwiched in between the inequalities, whether it's an and inequality or not. I know it's an or inequality, but just like with an and inequality, I do have two sentences here. I do have two cases I've got to solve, and so let's go about the business of that. So we're going to start here with 5j is greater than or equal to 15. Well, that's going to be easy enough to solve. All I got to do is divide both sides of the inequality by 5, and that's going to leave me with j is greater than or equal to 3. I did not have to flip or reverse or invert the inequality symbol because I was dividing by a positive. So I'm cool there. Let's go to the next side, and here I've got negative 3j is greater than or equal to 21. Well, to isolate the j, I'm going to divide both sides of the inequality by negative 3, but there I go. I'm dividing by negative 3, and so this is going to, rather than greater than or equal to, is now going to become a less than or equal to. And when I divide 21 by negative 3, that's going to give me negative 7. So I've got two statements here. J is greater than or equal to 3. And j is greater than or equal to negative 7. J is less than or equal to negative 7. And so this is an OR inequality. And so this is the union of the two inequalities. So let's go about and see how that's going to make a difference in our number line. So let's just put out here, let's say that this is negative 7 on a number line, and this is 3. So let's deal with this one first. So we got j is greater than or equal to 3. So first question is this going to be an open dot or a closed dot? Well, it's a greater than or equal to, so it's going to be a closed dot. Let's put a closed dot right here. And it's a greater than, so it's going to be extending out here to the right. Okay. So that takes care of that part. Let's take a look at the second one. Here we got j is less than or equal to negative 7. And again, open dot or closed dot? Well, the answer is going to be it's a closed dot because it's a less than or equal to negative 7. And so this is going to be represented by coming out here to the left of the negative 7. And so there we've got our solution set graphed on a number line. Now, one thing that this does, this kind of gets us into another lesson, but these are actually intervals here. So this could be an interval right here, and this is an interval right here, and this is an interval right here. And when it's an OR statement, if either of them make the statements, one of the statements true, then it is a valid solution. But what's not a solution is what would make both of them untrue. So let's see. If I wanted to verify this, I could test this interval right here. So what's between negative 7 and 3 that I could test? Well, I could test 0. How about that? So if I plug in 0 for 5 right here, if I plug in 0 right here, well, 5 times 0 is 0, and 0 is not greater than 15, so that's not true. And if I plug in 0 for j right here, well, negative 3 times 0 is 0, and 0 is not greater than or equal to 21, and so neither of those is true, and that's why it's left blank. That's why our solution sets are, as we represented, it's negative 7 going this way, greater than or equal to 3 going this way, and there we've got the solving of a compound inequality. Let's move here to another example. We'll move through it very quickly. Whether you like it or not, we're doing it. Well, let's take a look at here again. This second example, we're still solving an OR compound inequality. We're going to have to look at both inequality sentences and then graph accordingly. We're graphing the union of the solution set. In other words, that both solution sets would be true. So we start off here where we got G minus 6 is greater than negative 11. Well, my G's already isolated, so all I got to do is combine like terms. I'm going to add 6 to both sides of the inequality. And G, therefore, is going to be equal to, let's see, negative 11 plus 6 is going to give me negative 5. So G is greater than negative 5 is part of our solution of this compound inequality. Let's move to the second part. So here we got 2G plus 4 is less than negative 15. And we're going to start off here by subtracting 4 from both sides. So 2G is less than, see, negative 15, negative 4 is going to give me negative 19. And to isolate the G and finish this off, I'm going to divide both sides of the inequality by 2. So I got negative 2 divided by positive 2. Because I'm dividing by positive 2, I don't have to flip or reverse that inequality. It's going to remain a less than. Let's see, 2 into negative 19 is negative 9.5. All right, so I've got G is greater than this compound inequality when G is greater than negative 5 and G is less than negative 9.5. And let's see if we can't graph this. Let's get us a number line out here. And I'm going to put, let's put negative 5 right here. And let's put negative 9.5 right here. All right, open dot, close dot. G is greater than negative 5. Well, that's going to be an open dot. Let's change colors on this. That's going to be an open dot. And it's greater than, so my graph is going to come out here to the right of that negative 5, indicated by an open dot. And then we got G is less than negative 9.5. Well, again, that's a less than, doesn't have an equal to attached to it, so that's also going to be an open dot. And it is less than, so it's going to come out here to the left. It's a compound OR inequality. It's going to be the union of the two solution sets, bringing the entirety of both of the two solution sets into the overall solution set. And there we go. I am done. We have solved and we have graphed this OR compound inequality.